Welcome to Slider Chemistry Bites. In this video, I will be explaining the volumetric analysis technique known as titration. In particular, we will look at acid-base titrations, including the equipment setup, how the technique is used in the laboratory, sample calculations, and an introduction to titration curves. Titration is an analytical technique that can be used to accurately determine the concentration of an acid or a base solution using a neutralization reaction. The equipment we need for this technique includes a conical flask, and in this conical flask we have our analyte or our unknown solution, a pipette which delivers an accurate volume of our analyte, a burette which delivers a solution of known concentration, which is called the titrant or the standard solution, and finally an indicator which changes color when the analyte has been neutralized by the titrant. Let us consider the example of a hydrochloric acid solution of unknown concentration. The first step in titration is to deliver an accurate volume of the unknown acid, which is called the analyte. This is delivered to the conical flask using a pipette. This delivers a specific number of moles of the acid to the flask, which will be quantified using the neutralization reaction. In a neutralization reaction, there is a point where there are stoichiometrically equivalent moles of the acid and the base. This is called the equivalence point. For example, if we consider the reaction between hydrochloric acid, HCl, and sodium hydroxide, NaOH, we get a salt, sodium chloride, plus water. And in the balanced chemical equation, we can see that the molar ratios are 1 to 1 for the acid and the base. So once we reach the same number of moles of HCl and NaOH, we have reached the equivalence point. In titration, we can see the equivalence point by using an acid-base indicator which changes color as close to the equivalence point as possible. Where the indicator changes color is known as the endpoint of the titration. A few drops of the indicator are added to the conical flask with the unknown, and in the case of HCl and NaOH, we use phenolphthalein as an indicator. Phenolphthalein is a colorless solution in acidic conditions and is pink in alkaline conditions. To determine the concentration of HCl solution, we will need a sodium hydroxide solution of accurately known concentration. This is referred to as the standard solution or the titrant. This is carefully added to the analyte to accomplish neutralization. When the color of the solution in the conical flask achieves a permanent color change, the endpoint has been reached and the volume of titrant is recorded. Here in this diagram, you can see this. So here is the acid solution. It is colorless because it is acidic, and the phenolphthalein turns pink and is a permanent color change once the equivalence point has been reached. Once we have collected at least 3 trials, we can take an average of the volume. Here's some sample data where we have collected 4 trials. So let's take an average of this data, 12.1 plus 11.9 plus 11.5 plus 11.5 equals 47. And we'll divide that by the number of trials, 4, which gives us an average of 11.8. Now that we have this volume, which is in milliliters, we can convert this to liters, which is 0.0118 liters. We can then use the equation N equals C times V, where N is the number of moles, C is the concentration, and V is the volume. This will allow us to calculate the number of moles of sodium hydroxide, the concentration of the known standard solution of sodium hydroxide was 0.100 moles per liter. And we're going to multiply that by the volume in liters, which we take as the average volume of sodium hydroxide, which is 0.0118 liters. And that will give us 0.00118 moles of sodium hydroxide. Because the ratio of HCl to NaOH is 1 to 1, the number of moles of acid is the same as the number of moles of base in this neutralization. Therefore, we have 0.00118 moles of HCl due to a 1 to 1 ratio. With moles of HCl now determined, we simply need to divide the number of moles of HCl by the initial volume of HCl, which was 20 milliliters, in liters. This looks like this. This then gives us 0.059 moles per liter of HCl, which was the purpose of our titration. The titration process can also be shown visually in the form of titration curves. The process for generating these curves requires data logging software, a pH probe to measure the values as drops of titrant are added to the analyte. Here is a picture of such a setup. Here's a pH probe connected to a pH meter, and this would be connected to a computer which had data logging software. This would then record pH values as the volume of sodium hydroxide was added. As you can see, the data logging software plots pH versus volume of titrant. In contrast to the method previously described, this process requires that we go beyond the equivalence point until the curve flattens out. From these graphs, we can determine the exact pH of the equivalence point, which occurs at the inflection point of the curve. This can be seen in the graph as the middle of the vertical portion of the graph. So here's the vertical portion between these two lines, and you can see that this equivalence point is in the middle. The same for this graph of a weak acid, which is a little bit tighter. However, it is still the middle point of that vertical portion of the curve. You can also see that there's a difference in equivalence point when sodium hydroxide, which is a strong base, is titrated against a strong and a weak acid. A strong base, strong acid titration results in an equivalence point of 7, whereas a strong base, weak acid results in an equivalence point greater than 7. In this case, we can see it's 8.72. It's also important to note, although it's not shown here, that a weak base with a strong acid will result in an equivalence pH of less than 7. You'll also notice that the initial shape of the two curves is different. The strong acid curve is initially quite flat because the system is buffered against the addition of base due to the presence of strong acid in the solution. This results in water being produced and resistance to sharp changes in pH is accomplished. Thus, this section is called the buffer region. So we can see that buffer region here. The gradient of the weak acid curve is initially much greater due to the lower buffering capacity of the acid. This cannot resist changes in pHs as effectively as a strong acid can. In this section of the curve, a buffer system is being created between the weak acid and the strong base. This is followed by a flatter section where there is greater buffering capacity. You can see that initial part of the curve here. This is where the buffer system is being created. And here in this section is the buffering region. Another feature to note on these graphs is the half equivalence point. This is the point on the curve where half the equivalence volume has been added. On both graphs, that is 12.5 milliliters. It is about here. If we take this point on the curve, and in each case, we can extrapolate back to the pH, and on this graph, that pH at half equivalence is approximately 1.3. For the weak acid, at half equivalence, it's approximately 4.8. This is important because the pH at half equivalence is equal to the pKa. So pH at half equivalence is equal to the pKa, which is specific to that acid. And this can be useful in calculation questions involving acid dissociation, but this is another topic. I hope this video has helped you in your understanding of acid-base titrations. Until next time, go well. And give